probability events involving not. So our objective here, we want to find the probability that an event will not occur. And we're going to use this will not occur to find the probability of what we're looking for. I'll show you, I'll get more into that in just a few minutes. Let's talk about what we know coming in. We know the definition of probability. It's the chance that something, what we're calling an event, I should get rid of that letter D there, will happen. Okay, and we know that the probability of an event happening is always between 0 or 0% and 1 or 100%. If we have a probability of 0, that event is impossible, rolling a 7 on a die, for example. If we have a probability of a 1, that event is certain to happen. And we saw that the probability of an event happening is equal to the number of the ways the event can happen as a numerator divided by the total number of outcomes in the denominator. It's always a proper fraction between 0 and 1. If you remember, we found the total number of outcomes using the fundamental counting principle as necessary. And we learned that P with the event in parentheses is notation that says probability of the event happening. Okay, so now let's get into this word not, because it's sometimes a little easier to find probabilities if you understand the idea of not. So basically, an event will either happen or it will not happen. Okay? You're either going to roll a 5 on a die, or you're not going to roll the 5 on the die. You're going to roll something other than a 5, a 1, 2, 3, 4, or 6, for example. In weather terminology, it's either going to rain or it's not going to rain. Okay? There's no in between that stuff. So what this tells us is that the probability of the event itself plus the probability of not the event is going to equal everything. It equals the total, so it equals 1. We are certain that the event will either happen or not happen. Okay, that's a certainty, 100%. I'll roll a 5 or I won't roll a 5. Well, no kidding. There's a 100% chance of that. Now, with just a bit of math, if we subtract this section from both sides, we can make the following equation that is also true, that the probability of the event is equal to 1 minus the probability of not the event. Okay? And sometimes, so why do we care? Because sometimes it's easier to count up those things that are not what we're looking for than it is to count up those things that are what we're looking for. And if we can count up those things that are not what we're not looking for and then subtract that fraction from 1, we'll get the probability of what we are looking for. Let's take a look at an example or two. Okay. Let's make sure that I've got myself straightened out. Good. You throw 2 dice. Okay. What is the probability that the 2 numbers that come up are different? For example, you throw 2 dice, you get a 1 and a 2. Okay, well, what's the probability of getting 2 numbers that are different? Well, first thing, we don't know the total of outcomes here. We're not told the total of outcomes, so we need to figure that out, and that's our fundamental counting principle. Okay, so our fundamental counting principle leads us to find the total number of, I started writing the word outcomes before I wrote the word of. The total number of outcomes. And when we did that, we had the number of items or the number of things in our denominator, and we had the number of choices, not denominator, excuse me. We first listed the number of items or things we had, and above that we listed the number of choices, and then we multiplied. Well, we have two things here. So I'm going to create two underlines. Okay, this is going to be dice number 1. And this is going to be die, I guess I should say die, that's the singular, die number 2. I'm rolling 2 dice. So I have 2 items I need to work with, die 1 and die 2. Die 1 has 6 possibilities, 1 through 6. And die 2 has 6 possibilities, 1 through 6. So I have 2 items. The number of choices for die 1 is 6, for die 2 is 6. I put a multiplication sign between those, and I come up with the fact that there are going to be 36, if I can talk while spelling, B-I-L, there are going to be 36 possibilities from the roll of 2 dice. Okay, so now we have our denominator, total number of outcomes. So, what is the probability that the 2 numbers are different? Okay, so probability that they're different. Probability of them being different. Well, we know our total number of possibilities is 36. Well, how many of these are different? Okay, so up here are the ones we want that are different. Well, I'm going to start listing. I can roll a 1 and a 2. Obviously, a 1 and a 1 are the same. So I can't, that doesn't count, they're not different. I can roll a 1 and a 3, I can roll a 1 and a 4, I can roll a 1 and a 5, and I can roll a 1 and a 6, and then I can roll a 2 and a 1, 2 is the same, then I can roll a 2 and a 3, and oh my goodness, this is going to take a while, and so I'm going to kind of stay here. There's too many. I don't want to count all these up. I got 36 possibilities, and I'm only up through 1, 2, 3, 4, 5, 6, 7, and I got to keep going. I don't want to deal with that. That's too much work. Okay? So, as opposed to counting out all the possibilities that are different, I could say, well, wait a second. The probability that they're different equals 1 minus the probability that they're not different. So here's using the not to count probability. And of course, saying that they're not different implies that they are the same. In rolling terminology, we're going to roll doubles. Okay, so the probability that they're different is the probability that they're different plus the probability that they're not different is all the combinations, all 36. So the probability that they're different is equal to 1 minus the probability that they're not different. Okay, well this is equal to 1 minus. Total number of outcomes is 36. How many of these outcomes are not different or are the same? Well, I could roll a 1, 1. I could roll a 2, 2. Again, in dice speak, this is rolling doubles because these are all the same. And I have a 4, 4 and a 5, 5. And I'll bet you beat me that there are 6 possibilities in which I roll doubles. Okay, in which these are not different. So I put a 6 right here. And that's far easier than listing out or counting all of these possibilities. All right, so 1 minus 6 over 36. Of course, 1 is 36 over 36. 36 over 36 minus 6 over 36 is equal to 30 over 36. The probability they're different is 30 over 36, which simplifies. If you want that as a fraction, you have a 5 and 6 chance of rolling different. And as a percent, we can divide and multiply by 100, and that is approximately 83.3%. So the probability of rolling different, we used not to come up with that probability, and it would be 83.3% of the probability of rolling 2 numbers that are different. Let's look at an example with a table. Okay, I think I've got that straight for you. Okay, and this table shows the age distribution of 3,000 moviegoers in the U.S. Okay, so our total is 3,000. So guess what? We don't need the fundamental counting principle. We already know the total number of outcomes. And we have 4 age ranges broken down here. So we're going to select one moviegoer at random. What is the probability that her or his age is less than 65? Okay, well, so the probability of less than 65. Now this example is not quite as relevant as the first one, or not quite as obvious, because obviously if you look here, those that are less than 65, you add up this number plus this number plus this number and you're done. So we could do this as, well, I have 3,000 people. Those that are less than 65 are 900 plus 1080 plus 840. Okay, and then I haven't done this yet. Let's see. So I could do the math here and say this is 900 plus 1080 plus 840. That's going to be 2,820 out of 3,000. If I simplify that, let's just change it into a percent. Let's just go ahead and make this into a percent. So 2,820 divided by 3,000. That's going to be 94%. So we could do this particular problem fairly simply without using the not idea, but it does require that we add up these 3 numbers. You know, that's a step that's required here. Okay, now if you had a list of, maybe if you had 12 age ranges, adding up the 11 numbers would be more difficult, but in this case it was fairly simple. Or we could say the probability that they're less than 65, let's use that not idea, is 1 minus the probability that they're greater than or equal to 65. Because everybody is either less than 65 or greater than or equal to 65. So we'll take 1 minus all the others. Okay, well this one's a little bit simpler because we know we have 3,000, no adding required. The number that are greater than or equal to 65 is 180. Okay, and so we will do this, and with the calculator, this will also come up with, and it's actually precisely 94%. I don't need an approximately equal there. You'll also come up with 94. So an example here in which either way is probably okay, and there's not necessarily a huge difference in the amount of work. An example up here in which you do have a fair amount of difference in the number of work, counting up all the possibilities here when you know that rolling doubles is just 6 possibilities. But there's how you can use not to find the probability of something happening.